First move. I flip up the lever on the first WAGO, slide the brick's red +5V lead into position 1, and snap it down. Nice solid bite. I give it a little tug test, no wiggle. Now I make a short red pigtail. One end goes into position 2 of that same WAGO. Lever up, lever down. The other end lands on the breadboard's left red rail. Positive power now has a clean, shared hub. Next, ground. I open the second WAGO, feed in the brick's black GND lead to position 1, and lock it. Fresh black pigtail into position 2, and the other end goes to the left blue rail. Grounds are common to the whole board. Fuse time. I take the inline holder, pop in a low-value blade fuse for bring up, then connect it in series on the +5V path that runs from the WAGO toward the LED strip. That means WAGO, fuse, strip, +5V. It protects the LEDs and the wiring if anything shorts. I grab a short black jumper, double-check its ends, and plug one side into the left blue ground rail. Then bridge it over to the right blue ground rail. Nice and firm. Now every module will share the same reference. Next, I prep the LED power smoothing. I pick up the big 4700 microfarad capacitor. Find the long leg, that's positive, and the short leg, negative. I slide the long leg into the left red rail around column 3, and the short leg into the left blue rail. I press it down so the body sits stable and won't wiggle during tests. Okay, I'm powering only the 5-volt brick. I set my multimeter to DC volts. Black probe on the left blue ground rail, red probe on the left red rail. The reading settles at 5.521 volts. That's a little high. Normal with no load. Once the strip and amp draw current, it should drop closer to 5. I note the value, scan for heat or smell. None. Rails are steady, no flicker or sag. Power path is verified. I've got the breadboard in frame. Columns 1 to 30, top half A to E. The SN74 AHCT 125 straddles the center gap at columns 6 to 12. Notch pointing left toward column 1, so pin order is sane. Sanity check. Pin 1 is top left. First move. I enable gate 1 by pulling 1 OE low. I grab a short black jumper, land it on E6, and drop the other end into the left blue ground rail. Upper segment, right around column 6. Nice and tight so it doesn't flop on camera. OE is active low, so grounding it wakes that channel up. Next, I feed the buffer with the Pi's LED data. Green jumper from GPIO 13. That's physical pin 33, straight to 1A on E7. I give the wire a little service loop so it's not tugging the pin, then press it flat along the top half of the board. Now the series resistor. I'm using 330 ohms. One lead goes into C8, which is the same node as 1Y on E8. I use C8 instead of D or E, so the body of the resistor isn't crammed into the chip. Makes probing cleaner later. The other lead lands at A14. I like column 14 as my data exit. It's one small step beyond the chip footprint, keeps routing clean, and it's easy to remember. I grab a green jumper, same color as the signal line on the LED strip, to keep the logic path visually consistent. I anchor one end right into A14, nice and snug, making sure it seats cleanly in the tie point without wobble. The other end snakes gracefully off the board toward the strip's data in lead, the green wire on the SK6812 harness. Let's disabling the unused gates. The other 3 buffers on this chip aren't needed yet, so I'll park them safely. Their OE pins must be high to disable them. Starting with F7, that's 4 OE. I use a short white wire to tie it to the right red rail, which carries 3.3 volts. Then F10 That's 3OE, gets another white jumper to the same 3.3 volt rail. Finally, E9, 2OE, is physically closer to the left side. So for neatness, I run a red wire to the left red rail, the 5 volt side. Why the mix? Because any voltage above about 2 volts counts as a solid logic high for this chip. So either 3.3 or 5 volts works fine to keep those gates off. And I just pick the nearest rail each time to keep my runs short. Now for the A inputs of those disabled channels. I don't want them floating. I take F11, 3A, and F12, 4A, and tie them down with black wires to the right blue ground rail. Then E10, 2A, gets another black jumper back to the left blue rail. That grounds every unused input so nothing drifts or oscillates. Next are the power pins. E12 is ground. I hook that to the left blue rail with a black lead. F6 is VCC, the chip's 5 volt supply. Since the only 5 volt bus lives on the left side, I hop a red wire from F6 over to the left red rail. That bridge powers the entire IC from 5 volts, so it can output a full-strength signal for the LED strip. Before I ever power the Pi, I stop and meter everything. Ground probe on the left blue rail, positive probe on F6. I see about 5 volts from the bench supply. Then ground to E12, 0 volts, perfect ground. Same for E6, the enable pin. 0 volts means gate 1 is truly enabled. I grab a black jumper wire. This will carry ground. I look for pin 6 on the Pi header. That's the second pin on the outside row, near the corner. I gently push the black jumper onto that pin, and then plug the other end into the right blue rail of the breadboard. That ties the Pi's ground to the breadboard ground bus, so everything shares a common reference. Next up, I take a white jumper, because in my color scheme, white always means 3.3 volts. I find pin 1 on the Pi header. It's right next to the corner of the board on the inside row. I connect the white jumper there and then seat the other end into the right red rail on the breadboard. That brings the Pi's 3.3 volt line over so I can power all the low voltage logic and the Qwiic sensors. The Pi itself is still powered by its 27-watt USB-C supply, so I'm not feeding power back into it, just extending its rails outward. Once both jumpers are seated, I pause and check polarity. Red rail should be positive, blue rail should be ground. I take my multimeter, set it to DC volts, and touch the black probe to the blue rail and the red probe to the red rail. The display reads 3.3 volts, nice and steady. That tells me the connection's solid and that I haven't crossed anything. I pick up the little TSL2591 breakout. You'll notice it has 2 tiny JST-SH connectors, one on each side. Both are identical. That's one of the nice things about the Qwiic system. It doesn't matter which side we use, left or right. I grab a short Qwiic cable. It has that satisfying click when it seats. Black is ground. So I follow the black wire down to the Pi header and slip it on to pin 9, one of the ground pins. Then the red wire goes to power. But remember, in our color convention, red is 5 volts and white is 3.3. So this red lead actually lands on the right red rail, which is tied back to pin 1, the Pi's 3.3 volt supply. Next, the blue line SDA, the data line, connects to pin 3, and the yellow line SCL, the clock, connects right next to it on pin 5. Simple, clean, and no breadboard clutter. Now I boot up the Pi. When it's ready, I open the terminal and type sudo apt update and sudo apt install -y i2c tools. Once that's done, I make sure I2C is enabled. Sudo raspi config nonint do i2c 0. Finally, the fun part: testing. I2C detect -Y1. I watch the little grid appear, and there it is, 0x29, the TSL2591's default address. That tiny hex number tells me everything's alive and talking. All right, I've got the MAX 98357A board here, and the 7-pin header is ready. I'm setting it across row B, columns 20 through 26 on the breadboard. I press it in gently so each pin sits cleanly, no bends. Now from left to right, that's B20 to B26. Now I take the yellow jumper and slip it into A20, the hole just above LRC. That runs over to the Raspberry Pi GPIO 19, pin 35. That's the left-right clock line. Next, I grab a blue jumper for the bit clock. One end goes into A21, the other into GPIO 18, pin 12. Then the green wire for data in A22 up to GPIO 21, pin 40. That's the Pi's PCM D out feeding the amp's DIN. I leave B23, the gain pin, floating. That's default gain mode, which is fine for this MVP. Now the white wire. This one goes from A24, the SD or shutdown pin, across to the right red rail. That's our 3.3 volt line, keeping the amp always on for now. Power next. A25, the ground pin, gets a black jumper straight to the left blue rail. And finally, A26, the VIN pin, gets a red jumper over to the left red rail, carrying plus 5 volts from the WAGO connector. Now I'm grabbing the Dayton PC83-4 speaker. You can see the two screw pads marked out plus and out minus on the amp board. Those are my left and right hands in this moment. I loosen the tiny screws, slip the speaker leads in, red wire to out plus, black wire to out minus, and snug them down until they bite. I tug gently. Solid connection. Opening the configuration file. Sudo nano 4boot firmware config.txt. Classic move. I scroll down, enabling I2C and turning off the default audio. Then, I add the magic line, dtoverlay max 98357A. That's what tells the Pi to talk to our I2S amp. I save the file, exit nano, Control-O, enter, Control-X. Now the system needs a fresh start. Sudo reboot. The fan hums, LEDs blink, Pi goes quiet for a moment, then reconnects. Back in the terminal, I check the speaker output. Speaker test C2:TWL1. The command kits in, 48 kHz stereo, simple sine sweeps. I listen for that soft left-right pan from the little Dayton driver. When I hear both channels, that's the sound of the circuit breathing for the first time. I start by laying out the two WAGO blocks, one for 5 volts, one for ground. Then I grab the power supply's red 5-volt lead and push it firmly into the plus 5V block. Next, I take the LED strip's two red leads, the one from the female connector and the voltage-adding red, and seat them in the same slot. They click in snugly, joining the supply lead so all three share a solid 5-volt line. Now for ground, I move to the GND WAGO, take the supply's black ground wire and press it in. Then I bring both white ground leads from the strip, again, one from the connector, one from the voltage-adding tail, and lock them together with the supply ground. That parallel tie evens out the current and lowers resistance, making sure the start of the strip doesn't sag on voltage when it lights up. Before moving on, I tug gently on each wire to confirm they're secure. Then pause a second, listening for that quiet sense of readiness before power flows. I'm sliding the green wire from GPIO 13 over to GPIO 10. That's MOSI pin 19 on the Pi 5. This shift lets the LED strip run over the SPI bus, since RPI WS28X doesn't play nice here yet. I double-check the white 3v3 and black ground rails, make sure the level shifter's still powered at 5V, then press the wire in, flush, clean, firm click. I'm on the Pi now. Terminal open. I type sudo python led test spi.py. First, the strip flashes pure white, like a breath in. Then, one by one, red, green, and blue bloom in sequence. Proof, the data line's solid and timing's clean. I pick up the 16mm push button. It's a simple SPST, one normally open switch, so there's no polarity to worry about. 2 lugs, that's it, just a contact that closes when I press it. I seat the switch into its panel hole, snug and centered. Feels solid. Then I grab a green jumper. This will carry the signal. I connect terminal A on the button to GPIO 17, which is physical pin 11 on the Raspberry Pi header. Nice click when it seats. Next, I take a black jumper for ground. That's terminal B on the switch. It runs straight over to the right blue rail, my ground line. I could have landed it on any Pi ground pin, but tying it to the rail keeps things neat.